Hello, this is Tracy. We are going to test a hypothesis about a population mean. Our objectives are to determine if we can use the methods we learn in this section, conduct a hypothesis test to test a claim about a population mean using p-values, and interpret the conclusion of a hypothesis test in the words of the problem. And your homework is listed. We want to determine if we can use the methods we learn in this section. You won't be asked to do all of this for every problem, but in the real world, you'll need to, and there are several things that you can check on. For example, we're going to conduct a hypothesis test about a population mean. You need to make sure you have quantitative data. Your data needs to have a mean. If you don't have quantitative data, then you can't find a mean and you'd be doing something different. So you need to have subjects. For each subject, you need to count or measure something. You need to record that for every subject, and then you need to calculate the mean. Then you can use that data to test a claim about the population mean. We don't know if you have a random sample in all problems. If you're not told one way or the other, you have to assume you do. We don't know if you have a good study that has eliminated all of the sources of bias. If you don't know, if we're not told either way, we have to assume so. We do need to check that one or both of the following are true. Either your population needs to follow a normal distribution, or you need to have a sample size greater than 30. If one of those two things is not true, we would need to use other methods. If you had a bad study, well, then you shouldn't be doing any analysis because bad study leads to meaningless results. But if you have a study with a small sample and your population is not normally distributed, there are other techniques that you can use to conduct a hypothesis test, just not what we're going to learn in this class. Now, which method we use to conduct our hypothesis test depends upon whether we know the population standard deviation or not. Remember, the central limit theorem tells us that a population has a mean. There is a mean for quantitative data that the population has. The sampling distribution of the means is a normal distribution. It clusters around that true population proportion, and the standard deviation is sigma divided by the square root of n. Population standard deviation divided by the square root of the sample size. If you know the population standard deviation, then we can use that normal distribution, that z distribution, to conduct our hypothesis test. We'll use what's called a z-test in our calculators. If we don't know the population standard deviation, we can't get at that normal distribution that represents the sampling distribution of the means. But we can approximate it with something we call the student t-distribution. So we will use what's called a t-test to conduct our hypothesis test of the population mean. A t-distribution is similar to a normal distribution, but the tails are fatter because we don't know the standard deviation, so we don't really know what the mean of that distribution is. Things get a little weirder, but we can still do something. We just use a different test. So here's the problem that we're going to do. An engineer designed a valve that will regulate water pressure on an automobile engine. The valve was tested on 170 engines and the mean pressure was 6.4 pounds per square inch. Assume the population standard deviation is 0.9 psi. If the valve was designed to produce a mean pressure of 6.2 psi, is there sufficient evidence at the 0.01 level that the valve performs above the specifications? Before we get started, figure out what we're trying to do and can we do it with what we're going to learn in this class. So look for the this is what you do, or here is the question sentence in here to figure out what we're trying to do. Is there sufficient evidence at the 0.01 level that the valve performs above the specifications? When we see something like, is there sufficient evidence? Well, that sounds like, and it means we are making a claim about the population parameter, and we want to gather evidence to test that claim. We want to test the claim that the valve performs above the specifications. And our specification is a mean pressure of 6.2 psi. So we are trying to conduct a hypothesis test of a population mean. So verify what we can. Is our data quantitative? Well, yeah, we're given a mean. That means we have quantitative data to begin with. Do we have a random sample? We don't know. We hope that the engineer, the researcher, the quality control department, whatever, gathered a random sample, they eliminated sources of bias. We hope. We're not told. We have to assume so. Does our population follow a normal distribution? I don't know. Probably. These are manufactured items, and most of the characteristics of manufactured items do follow a normal distribution. We don't know, but we do know the sample size is greater than 30. We're testing 170 engines. So yes, we can use the techniques that I'm going to show you, and that your book shows you, and the homework shows you, and all that good stuff. All right, so here is just saying what I said in the last slide. Is there sufficient evidence is asking us to test a claim about the population mean. So hypothesis test for a mean. Data is quantitative. We have a mean, so we must have quantitative data. Don't know if the sample's random, don't know if it's a good study, but we do know the sample size is greater than 30. So if the researcher did his job, we can do ours and analyze. We are going to follow the steps that some of the homework problems give you for practice. However, not all of the homework problems and not all of the exam questions will walk you through step by step. You may need to conduct the entire hypothesis test just from the problem given, the paragraph a couple of slides ago. So you may want to write these down or summarize them or something along those lines. First step in the homework problem is to determine the hypotheses. This is what we did in the last section. This is what we practiced before. Find your null and alternative hypotheses and formulate them correctly. The homework asks you to find the value of the test statistic. We're going to do that using our calculator, but here really what we're going to do first is decide the type of test. Are we going to conduct a Z test or a T test? And then we'll come back and find the value of the test statistic. Specify if the test is one-tailed or two-tailed. We use our alternative hypothesis to tell us this, and this helps us figure out how to conduct the test in our calculator. Find the p-value of the test statistic. That is the probability of getting our results if the null hypothesis is true. And again, the calculator will do this for us as long as we pick the correct test, enter the correct information. Identify the level of significance for the hypothesis test. We call this alpha. And yes, this is pretty much the same alpha that we saw when we were finding confidence intervals. This is how rare our results, how unlikely our results need to be for us to say, we're not so sure about that null hypothesis. Based on our level of significance and our p-value, we make a decision to either reject the null hypothesis because we don't think it's very likely that that null hypothesis is true given these crazy results we got, or fail to reject. Hey, we don't know that the null hypothesis is true, but our results, yeah, it's pretty much what we'd expect with the null hypothesis, so why not? Then, and this is not the last step in most of the homework problems. Some of the problems have this as a multiple choice. I will ask you to write this up in the exam. Interpret the conclusion of a hypothesis test in the words of the problem. None of your calculations mean anything if the end result that you go to your boss with is backwards. So we're going to make sense of our results. So step one, determine the hypotheses. Remember, your null hypothesis is an equation about the population mean that is based on the status quo, the common wisdom, the previous claim that some other researcher found, the design specifications, the manufacturer claim, something that we just assume unless we have reason to believe otherwise. And the alternative hypothesis is the competing claim. This is what we think might be true instead of the null hypothesis, and that is always given as an inequality. So in our problem, we are told that our valves are designed to have a mean pressure of 6.2 psi. So that's our null hypothesis. That's our assumption. That's what we should accept as being true, except we never say accept, we never say true. But unless we have reason to believe otherwise, that's what we're going to go with. Our competing claim: is there sufficient evidence that the valve performs above the specifications? That's our alternative hypothesis, that the true population mean for these valves is greater than 6.2 psi. Now, step 2. What type of test are we conducting? And then we're going to actually go do that on our calculator and come back and give this test statistic. So the type of test, well, it depends. Do we know the population standard deviation or not? Our problem tells us, assume the population standard deviation is 0.9 psi. We are given sigma. That means we are conducting a hypothesis test about a population mean where we know the population standard deviation, we know that sampling distribution of the means, we know that normal distribution, it's a z distribution, use a z-test. Is our test one-tailed or two-tailed? So here, what we have is we have that normal distribution that represents the sampling distribution of the population means. So our population, if the null hypothesis is true, has a mean. Our valves have a mean pressure of 6.2 psi. So that goes right there at the peak, the center of our sampling distribution of the means. Most of the means will be clustered around that 6.2 psi. The farther away you get, the fewer samples will have that mean. So if you look at a sample mean of 6.4, look at that tail. 6.4 or above, ooh, that's a tiny proportion of the area. Most of the samples are going to be clustered around the middle. Only some of them, only a small percentage of them, have means that are so high that it's 6.4 or above. That's just a little bit of area under the tail. And since our alternative hypothesis is the mean bigger than 6.2, we are only looking at that right-hand tail. So this is a one-sided test, a one-tailed test. We call it a right-tailed or a right-sided test. Now we want to find the p-value of the test statistic. We want to find the p-value for the results that we got. And the p-value is the probability of getting our results or more so if the null hypothesis is true. If the p-value is high, then that says the probability of getting our results, if the null hypothesis is true, is pretty high. If something has a high probability, that means it's not unusual, it's not unexpected. We would expect to get those results if our null hypothesis is true. So we have no reason to suspect that there's anything wrong with the null hypothesis. If we have a high p-value, then our results are close enough to the null hypothesis that we figure, yeah, null hypothesis is probably just fine. If, on the other hand, our p-value is low, then that says the probability of getting our results, if the null hypothesis is true, that probability is low. Our results are not likely, they are unexpected, they are unusual. So either we got one of those freakish samples in the tail of our sampling distribution, or maybe there's something wrong with our null hypothesis. Now remember from the last section, we never say the null hypothesis is true or false. We never accept anything. we just reject or fail to reject. We support or fail to support. We never know truth just from a hypothesis test. We have to do more, but we can support or fail to support. Now to find that p-value, we're going to use our TI. And here's the video for using the
All
TI
right,
to find
let's
the
go
p-value.
ahead and conduct a hypothesis test for a population proportion. So again, for hypothesis testing, just like with confidence intervals, we go to our favorite button in the stats class, STAT. Again, just like with confidence intervals or any other hypothesis test, we arrow over to tests. In this case, we are conducting a hypothesis test about a population proportion. We are testing a claim about what proportion or what percentage of a population has a particular characteristic. So for this, we are going to use the, wait for it, yes, the one proportion z-test. And it's a z-test because we are using a normal distribution to approximate the binomial distribution you get anytime you are dealing with a proportion. What percentage of successes do you have? So, number 5. And we just need to go ahead and fill in the pieces. In this problem, the null hypothesis is the claim that the population proportion is 30%. So P0 or P0, that thing right here, first thing, is what we claim in the null hypothesis is the population proportion. 30%, 30 divided by 100 is 0.3. All right, X is the number of successes, and in this problem, we have 63 girls who said they smoked to stay thin. Oh, depressing, isn't it? All right. And the number of trials. We looked at 273 randomly selected, teen girls living in Massachusetts. Now here, we are going to put the symbol that we use in our alternative hypothesis. We are testing the claim that the true proportion, the true percentage as a decimal point, is less than 30%. That's what we're given in the problem. That's what we used for our alternative hypothesis. Arrow over and then enter so that we are on, that's not less than, try that again, less than, okay, that's what we want to be. Our alternative hypothesis is that the true population proportion is less than 30%, is less than this P0 we claim in the null hypothesis. Now arrow down, arrow over to draw. Go ahead and draw it. And here are the results we will talk about on the next screen.
And here is the results that we get when we use our graphing calculator to find our test results. Now here we have our normal distribution. We really can't see it on this picture because look how tiny our p-value is. Our p-value is 0.0019. That's a tiny number. That's what? That's almost 2 out of 1,000, 1 out of 500 chance of getting our results. That is a tiny shaded area, so tiny you can't see it. Now, if your p-value, if your shaded area is so tiny you can't see it, that means your results are pretty unlikely. You're not likely to get your results if the null hypothesis is true. If your shaded in area is huge, if you see tons of blue on the screen, then that means, well, yeah, we expected to get those results. That's perfectly normal given the null hypothesis. This is tiny. So there's our p-value, 0.0019. Our test statistic is a z statistic, and it is 2.8974. That tells us that our sample result of 6.4? Yeah, 6.4 psi is 2.8974 standard deviations above the mean of 6.2. That's a lot of standard deviations away. So, our p-value tells us the probability of getting our results of 6.4 psi or higher is 0.0019 if the null hypothesis is true. This is a small probability. Either we've got very unusual results, we got the freakish sample, or the null hypothesis is not true. There's our test statistic. It's a z statistic, 2.8974, round to 2 decimal places. So 897 rounds to 90, and we write that as 2.90. That shows we rounded to the nearest hundredth, not the nearest tenth. So again, that means that our sample mean is 2.90 standard deviations above the mean of the sampling distribution, which would be 6.2 if the null hypothesis is correct. Now that doesn't seem like it's that many standard deviations away. Hey, our population standard deviation was 0.9. Remember, central limit theorem says the sampling distribution of the means has a standard deviation that is sigma over the square root of n. We have a huge sample. That means the standard deviation for this sampling distribution is small, 0.069. Now, we are going to identify the level of significance for our hypothesis test. This is called alpha. And you really should do this before you find your p-value. Don't know why our homework does it after. Because the alpha, the significance level, tells us how unusual our results need to be in order for us to say, hey, we're not so sure about this null hypothesis. Is 5%, a probability of 5% or less, unusual enough? Is a probability of 1% or less unusual enough? Do we need our results to be freakishly unusual, like 0.5%, before we say, this null hypothesis, we don't really believe it? That's what alpha is. It's how sure we want to be that our results are really unusual. We want to choose that before we find a p-value. Otherwise, we might be tempted to say, hey, I got a p-value of 4.5. I don't want my alpha to be 1%, 0.01, because, well, then my results aren't unusual enough. But hey, let's make my alpha 5%, 0.05, then a p-value of 0.045. Ooh, yes, my results are significant. Now, you choose your significance level in advance, then you find your p-value, then you compare. So we are told in our problem, is there sufficient evidence at the 0.01 level? That tells us, that 0.01 level tells us that alpha is 0.01. That means we need a probability of 0.01 or less before we say our results are too unusual to think the null hypothesis is okay. And remember that 0.01 is 1%. Based on our alpha and our p-value, we either reject or fail to reject the null hypothesis. We reject the null hypothesis if our results are too unlikely if the null hypothesis is true. And alpha tells us how unlikely our results need to be. Our alpha is 0.01. That means we need our results to have a probability of 0.01 or less. Remember, the lower the probability, the more unlikely to reject the null hypothesis. If our p-value is less than alpha, we reject the null hypothesis. Our p-value is so low, our results are so unlikely, that we don't really think that null hypothesis is true. We never say that. We never say true or false. We reject it, though. So our p-value is 0.0019. That is less than our alpha of 0.01. We reject the null hypothesis. Our results are too unusual. Our probability of getting our results is too low if the null hypothesis is true. So what does that mean in words? Well, our null hypothesis is that the valve produces a mean pressure of 6.2 psi. We reject this claim. Our alternative hypothesis is that the valve performs above specifications. So our data supports this alternative hypothesis. Our data does not support the null hypothesis. And we could say this in the words of the problem in a couple of different ways. I'm going to give you 3 different ways. There are others. Just get the meaning across. Our data does not support the claim that the valve produces a mean pressure of 6.2 psi. Our data does support the claim that the valve performs above the specifications of a mean pressure of 6.2 psi. We have sufficient evidence to support the claim that the valve performs above the specifications of a mean pressure of 6.2 psi. So again, these are just a couple of different ways of saying the same thing. What does it mean to reject our null hypothesis? Now, if we don't know our sigma, we do not have a population standard deviation, you would do everything exactly the same except on your calculator. When you go to stat tests, instead of choosing the z-test, we would choose the t-test. Instead of inputting sigma, a population standard deviation, you input S, a sample standard deviation. Otherwise, repeat. All right, as always, if you have questions, please, please, please let me know.